on page
238. No. Probably not.
Ocean acidification is what we're on page 236. This was, do y'all remember what this is called?
Coral bleaching.
Coral bleaching. So that it happens whenever the pH of the water gets too low and the algae die. Also, pollutants can cause it. There are some types of fishing where they squirt poison in the water to kill fish, and it'll kill the corals. There's a lot of different ways that this can be caused, but one of the main ways is by the changing of the pH in the ocean. And do y'all remember why it changes?
Due to acid rain.
Yeah, due to things like acid rain. And why is there acid rain?
Because of pollution.
One of the things global warming does is it you have a higher amount of CO2 in the atmosphere, and the carbon dioxide reacts with water to form carbonic acid, and so that'll change the pH of the ocean. And so these things are very sensitive to pH changes. This is a little video on that I didn't get to show you.
The brown coloration of healthy coral is due to microscopic algae called zooxanthellae that live within its tissue. The coral has a special relationship with these algae called a symbiotic relationship. The coral acquires food from the algae, and the algae receive a safe place to live. However, if water temperatures rise, corals become stressed, and this relationship begins to break down. The zooxanthellae begin to leave the coral tissue. Without its resident zooxanthellae, the polyp tissue is transparent, and the white limestone skeleton beneath becomes visible. This process is called bleaching. Coral polyps, now a ghostly white, are still alive. If normal temperatures return in time, they can recover their symbiotic algae and return to health. However, if the water remains too warm for too long, the polyps will starve and eventually die. Within a few days, the dead coral skeleton becomes coated in plants that move in to fill the space. Other reef creatures that have zooxanthellae in their tissue, such as giant clams and anemones, are also known to bleach under these stressful conditions. If stressful conditions, such as high water temperatures, occur over large areas, the reef may experience a mass bleaching event. The Great Barrier Reef has suffered from several mass bleaching events, with between 60 and 95% of reefs in the marine park being affected during some years. Most reefs have survived with relatively low levels of coral death, while some locations suffered severe damage, with up to 90% of corals killed. Full recovery of badly damaged reefs will take many years, even decades. Corals and reefs are, to an extent, resilient to the impacts of coral bleaching events. However, if coral reefs are continually subjected to the impacts of severe bleaching and other disturbances, their resilience or ability to recover is likely to diminish.
So with the corals at the bottom of the food chain, there are a lot of fish that eat coral, like the parrotfish. Remember, it's got that beak in front of it, and it can just kind of chip away at the coral and eat it, and then things eat the parrotfish, and so you've started the food chain there. So with the amount of corals going down because of bleaching, that affects all the fish in the ocean. And like I've said many times, it's estimated that there's only about 10% of the fish left in the sea that there used to be. So that is a major extinction event. It's when the meteor hit the Earth and killed all the dinosaurs, it killed about 70% of the species on Earth. This sort of global warming thing, and human impact and pollution and all that, is killing at that rate or higher. this is a graph showing that as human population has increased, we have increased our level of our use of fossil fuels, our amount of nitrogen. This is the total nitrogen here that's created in red. Ammonia is a form of nitrogen. And so creating these huge amounts of nitrogen has caused all sorts of problems. Nitrogen is used by humans as a fertilizer. It also comes out of burning fossil fuels. You get car exhaust that releases nitrogen. And the nitrogen can have all sorts of effects. When nitrates get in the air, and when we talk about nitrates, we talk about NO2 and NO3. These are pollutants that come out of your car exhaust. They come out of when you burn coal and stuff for power plants. Releases these pollutants. They get in the atmosphere. They can also combine with water. Both of these can combine with water. And then you form something called nitric acid. And again, the nitric acid can come raining down and cause acid rain problems. Another thing, you have nitrogen in your fertilizer. And when you fertilize fields and such, the nitrogen runs off. When it rains, the rain pulls the nitrogen off the fields, and the nitrogen will run into the water and cause algae blooms in a process we call eutrophication. So this is smog. Have you ever seen a smoggy city? Mexico City has a big problem with smog. Los Angeles sometimes. I've been to LA and I've seen just brown air there. It just kind of hangs over the city.
And then, one other thing about the fertilizer thing, it can also flow, during a rainstorm, it can flow into the driveways and then onto the roads, which flow into the drainage system.
Into the sewage system.
And drainage, it's many water drainage systems that are on the sides of the streets, and those flow directly to the ocean. Where where sewage systems, it's a separate thing, connecting houses.
Right. And then it pulls all that material, which is a lot of nitrogen, into the water, and you get this process that we call eutrophication. This is an important process. What will happen is all this nitrogen running into the water, it acts to cause these the algae that's in the water to multiply. The algae takes those fertilizers and runoff and uses it to grow. And in a lot of areas, it'll grow like crazy. And you see all this green algae here. And then the next thing that happens is the algae will die, and their dead bodies will float to the bottom, and they'll be decomposed by bacteria and fungus at the bottom of the ocean. And the decomposition process uses oxygen and removes oxygen from the water. And so whenever you see a lake like this, that with a lot of algae on it, or a river, what happens is it becomes depleted of oxygen. And fish can't live in low oxygen levels, so the whole area doesn't have any fish in it. And these are especially, you don't usually see areas like this. This is an incredibly eutrophicated area. But it can happen in the ocean too. There are these giant dead zones, what we call anoxic dead zones in our oceans, where there's not much oxygen in the water, not enough for fish to live. And so the amount of fish and the amount of shrimp are very, very low.
Isn't the Red Sea just like an overproduction of dinosaurs?
I don't know. Is it?
Didn't we learn about that?
The Red Sea? It might be. Here's a funny little animation about it. These are all areas of where we've had algae blooms. And another thing that these algae blooms can cause when you have you ever, we studied about red tides.
That's what I meant. I said Red Sea, but I meant red tide.
Oh, okay.
Overproduction.
I thought you were talking about the Red Sea.
No, I meant to say
Yeah,
red tide.
red tides are where these little tiny microbes, dinoflagellates, they multiply like crazy. You get too many of them, and everywhere where you see red dots is areas where you have red tides, and red tides can kill people. If a person swims in it and takes in these poisonous substances that are released by these algae, they can die, and it causes huge fish kills. Here's the amount that you had in 1970. Everywhere where you see a red dot is where there was a red tide. And here was 2000. You can see it's vastly increased because there's more people and we're producing more fertilizers and there's more runoff. You gotta grow more food if you have more people. So there's more farms and more fertilizers and such. Here is the Gulf of Mexico hypoxic zone. So this is an area in the Gulf of Mexico where the amount of oxygen in the water is extremely low. Hypoxic means low oxygen. Hypo means under. Y'all know that term, hypo? Like a hypodermic needle goes under the skin. Hypoxic is low oxygen. And look at this huge area. And the reason why it's right there is because these rivers, the Mississippi River and the Ohio River and all these rivers all feed down here and come out there. The water comes out right here in the Gulf of Mexico. Well, where it comes out, I mean, all the fertilizers from all the fields, all the farmlands, all get dragged off by rain, or all go out right here. And the amount of algae, the algae overgrows in this area of the ocean, and then the amount of oxygen goes down. Here's a little thing on that. Marine biologist studying it.
Divers down and flag up. These divers are replacing oxygen meters underwater with new ones, gathering information on oxygen levels at different depths. Underwater, the meters are attached to a buoy anchored at the bottom.
And a buoy that's near the surface and a cable strung out in between, and on it we have 3 oxygen meters.
Today, they're diving about 25 miles southeast of Terrebonne Bay. Heading up the hypoxia zone research is Dr. Nancy Rabelais of Louisiana University's Marine Consortium, or LUMCON. She and her assistants, Laura, Adam, and Kyle, make regular monthly trips out here to check numerous stations, from Terrebonne Bay all the way to the Chacalaya area.
Well, we started studying it in 1985. It was obvious that there was some low oxygen out here, that nobody really knew how widespread it was or how persistent it was. So some initial funding from NOAA provided the opportunity to document that.
When water contains less than 2 parts per million of dissolved oxygen, it is termed hypoxic.
The Mississippi delivers nutrients, phosphorus and nitrogen, and they stimulate the growth of the phytoplankton that make the water so green today. And the more nutrients that are delivered, the more the phytoplankton grow. And that decomposing phytoplankton, when it sinks to the bottom, the bacteria that decompose it use up the oxygen, and that leads to the low oxygen on the bottom.
The majority of phosphates and nitrogen that arrive in the Gulf are from runoff in the Midwestern states. In fact, about 41% of the country's area drains into the Mississippi River. Last year's hypoxia zone looked like this. In fact, it's been growing throughout the years. Also, the size of the area may be diminished if hurricanes or tropical storms stir up the water and, of course, the oxygen. One of the adverse effects of the lack of oxygen in the water is the drastic depletion of shrimp and bait fish, which in turn hurts the fishing and shrimping industries.
Fish like red snapper, red drum, croaker that depend on feeding on the bottom have to move out of the area. The brown shrimp, white shrimp move out of the area, so that the only fish that you'll see today will be up in the water column.
Hopes are that one day, through research, the amount of nitrogen and phosphate can be reduced, thereby reducing the amount of low oxygen levels in these waters, making this area continue to be one of the best shrimping and fishing spots in the entire United States. Reporting from the Gulf of Mexico, I'm Bill Sherman for This Week in Louisiana Agriculture.
It's almost as big as fun.
Gotta even give them. So that hypoxic zone is really the reason why they show the relief map here is it really sits down low in the ocean. It's near the bottom. But that's where there's a lot of fish down there, you know, so it really hurts your fishing industry. Fish can sense when there's not enough oxygen, and they just don't go to places where there's not much oxygen. And same with shrimp, and you know, all these organisms, they just leave the area. This is a graph showing the number of hypoxic zones in the country. Hypoxic means below 2 parts per million dissolved oxygen. And you can see how it's gone up. This only goes through 1990, so that was 20 years ago. Almost 70 hypoxic zones where there were none in 1940. So, and who knows what that is now? I'd like to see more recent info. Doesn't that look like a logarithmic growth? Who's that? Question?
One other thing, lakes and ponds and things like that, they're also more vulnerable at oxygen depletion because of the lack of running water.
What did you say are more vulnerable?
Lakes and ponds.
Oh, lakes and ponds. That's right. That's right.
Yeah, and not just the fertilizer, but also if a whole bunch of leaves fall into lake or pond, when those decompose, they also take up oxygen as well.
Mm-hmm. Yeah, if you have an isolated area that doesn't have new water flowing in it, then you can't have any turnover. So that's why you see these. These are all lakes and ponds that have really just got a ton of fertilizers and decomposition going on in them.
There's the chart in the book has more like recent.
Oh, it has more recent data?
Oh, it's right there.
Yeah, this is just the Gulf of Mexico hypoxic zone. So this shows, because they've been doing research there for quite a while. The other one was just the total number of hypoxic zones found anywhere. So you can see it fluctuates. And one of the reasons why it fluctuates is if a big hurricane comes through the Gulf of Mexico, it'll stir up the water, and that'll deliver new oxygen to the water. So a hurricane is actually good for a hypoxic zone. So maybe in 2000 there, we had some big hurricanes come through, and that's why it wasn't as big.
When was Katrina?
2004.
4.
That's 04, so it was pretty big there. Another problem associated with humans is the ozone hole in the Antarctic. Now, for quite a while, people have been producing chemicals. Where's my eraser? Never an eraser when you need it. Yeah. People have been producing chemicals called CFCs. You know what CFC stands for? Chlorofluorocarbons. When they first came out with these, they were said to be miracle chemicals. They could do a lot of things that we need to happen as far as our industries go. They were used in spray cans. Hairspray, yeah, if you spray bug spray and that kind of thing. They were also highly used in electrical transformers. You know those things that look like little trash cans that you see on a telephone pole? Those are transformers. And they pump these chemicals into those transformers and they help reduce the amount of energy coming into your home. And then another place they were used in air conditioners and refrigerators. And so in the 1920s, 30s, 40s, 50s, we were using these chlorofluorocarbons like crazy. And what scientists didn't realize is that the chlorofluorocarbons would leak out, these molecules would leak out molecule by molecule from the refrigerators and from the transformers and from the spray cans, and they would float up into the upper atmosphere. And in the upper atmosphere, these chlorofluorocarbons, see, they contain chlorine, Cl, and fluorine. And these chlorine and fluorine atoms act like enzymes. They tear apart the ozone molecules one by one. So an O3 is an ozone molecule. And we have, protecting our Earth in the upper atmosphere, an ozone layer. Have we talked about the ozone layer yet in this class? How many are familiar with the ozone layer? Raise your hand if you've heard of that before. Okay. So there's an ozone layer protecting our Earth, and just molecule by molecule, these chlorine and somewhat fluorine atoms will tear apart that O3. And we started to lose this ozone layer. And that's bad because the ozone layer protects us from the sun. And without an ozone layer, if you went outside and laid out in the sun, you'd be killed in just a matter of minutes. It would be a heck of a sunburn. And so, if we lost our ozone layer, every living thing on the surface of the Earth would be killed. And so that's a problem. And some scientists started studying this, and they noticed with their equipment a hole in the ozone layer developing over Antarctica. And this is a measurement of the hole in the ozone layer.
Why would it be over Antarctica?
Well, that's not an easy question to answer, and it has to do with the way the Earth spins and the location of the oceans and the land on the Earth. These molecules, because the Earth is spinning, tend to move toward the poles. If the molecules are over warmer lands, they kind of dissipate. But if it's over a colder area, they'll kind of stay there. And so they tend to collect over Antarctica. And the warmer lands will kind of keep them from collecting over the North Pole. And so every winter, we build up these chlorofluorocarbons down here, and they tear up the ozone layer. And then as spring comes around, you have this kind of hole in the ozone layer open up down here. And then the way the weather patterns are, it kind of dissipates and the hole closes up as you go through the summer and fall. And then it opens up again back in the winter. And so they've been measuring, scientists have been measuring the size of the ozone hole, and it was getting bigger. And this is alarming, of course, and people got scared, and all the countries of the world came together and they said, look, we need to stop producing these chlorofluorocarbons, and we phased those chemicals out, and we're using different chemicals in place of it that work. And it was kind of a thing that all the countries of the world got together and did, and now the ozone layer is kind of stabilized, and they think that it will, they know it naturally repairs itself. The ozone reforms over time, and they think that maybe in 100 years or 200 years, the ozone layer will be completely rebuilt and back to about what it was before. They think that will happen. But you can see it has kind of stabilized here. It seems to be not increasing like it was. Look what it was doing, how big it was getting. This shows the size of the ozone hole. This dark area here is the ozone hole as it's gotten bigger from 1980 all the way to 2000.
Does it affect animals that live there?
It could, except for a couple of things. You don't have direct sunlight when you're on the South Pole because the sun is at such an angle, so it's not too bad there. And there's not hardly anything living there.
Yeah,
so for those two reasons, you don't see much effects of it. If for some reason the world were situated differently and the ozone hole was right over North America or something like that, then you'd see a lot of bad problems. We already see, because there's a hole here, but there's ozone depletion throughout the world. It's not like the ozone is exactly normal here. It is less here, and we have seen higher rates of skin cancer because of ozone depletion than there used to be. So there is some depletion everywhere, it's just more depletion at the South Pole. So ozone depletion has already killed folks. Surely more people got cancer than would have if we had more ozone layer. And they're already dead from it.
Doesn't it block out like UV rays?
Ultraviolet rays, yeah, the same thing that gives you sunburns. That's what's blocked by ozone. Some UV rays get through anyway, and so you can get a sunburn, but most of them are blocked. If you went out in a spaceship and went above the ozone layer and were unprotected up there, a spacesuit protects an astronaut from it, but if you're unprotected up there, you'd get sunburnt really, really quickly. And like I say, it wouldn't take you too long to die from the ultraviolet radiation. have some video footage here. This shows the chlorine, how it reacts with ozone to form ClO and O2. So it's torn apart the ozone molecule.
So nothing has those chemicals in it?
There are a few things that do, but most things don't. We've pretty much phased those chemicals out. Here's an ozone depletion study.
Over here we've got the Clean Air Facility operated by National Oceanic and Atmospheric Administration.
Thousands of miles from factories or cars, scientists monitor some of the cleanest air in the world and establish clean air standards. They are also working to understand a phenomenon that occurs over Antarctica every winter, a thinning in the ozone layer known as the ozone hole. This is John Lynch, Director of Atmospheric Studies at the South Pole Station.
Okay, so what is the problem with ozone over Antarctica?
Well, during the springtime, which here, of course, is September, October, November, it disappears pretty much. Two-thirds of the ozone over the continent disappears each spring.
These infrared images taken by satellite show a hole in the ozone layer over Antarctica. In recent years, the size of this hole has exceeded the size of the United States.
Is ozone depletion a big problem in the world? What is its magnitude?
Well, if there were no ozone layer, there'd be no life on Earth. I mean, well, at least not on the surface of the Earth.
Scientist Rick Ramos is one of the 20 people who will remain at this station all winter, living in 6 months of complete darkness with little contact with the outside world. His mission? To use special balloons attached with recording devices to monitor the depletion of ozone over Antarctica.
As it goes through the atmosphere, it will be giving us data through the transmitter. Once it reaches altitude, about 8 millibars or 100,000 feet, the balloon will actually burst, and the parachute will deploy and it will fall back to Earth. All the while, it's still giving us descent data.
Ozone forms in the stratosphere, 10 miles above the Earth's surface, when sunlight collides with molecules of oxygen. The resulting ozone serves as a protective layer, shielding the Earth from the sun's harmful ultraviolet rays. But in recent years, some scientists believe that in certain parts of the world, the ozone layer is thinning, and we're in danger of losing this natural sunlight.
The main cause of the ozone destruction here is from chlorine reactions. Most of the chlorine in the atmosphere comes from chlorofluorocarbons, which are used as refrigerants and propellants and aerosols and so forth.
When chlorine comes in contact with ozone in the stratosphere, a chemical reaction occurs that destroys the ozone, allowing the sun's harmful ultraviolet rays to reach the Earth, exposing us to radiation that has the potential to cause skin cancer. I helped Rick Ramos launch one of his ozone balloons.
Okay, ready on 3. 1, 2, 3. Yeah, that was a good one.
All right, now that we let the ozone balloon go into the atmosphere, we're going to go upstairs to the computers and actually get the information that the instruments are transmitting.
We'll monitor the actual data coming from the balloon we just launched right now.
Some scientists believe that ozone thinning is accelerated over Antarctica for 2 reasons. Due to the extreme cold in the winter months, clouds containing ice crystals form in the stratosphere over Antarctica. Chlorine molecules attach themselves to these ice crystals. The result, ozone is destroyed. Antarctica's ozone problem is further complicated by the presence of the circumpolar vortex, circular winds that swirl above Antarctica during the winter. The outer edges of these winds create an impenetrable barrier that prevents new ozone from entering the stratosphere above Antarctica. So in winter, when ozone is destroyed over the continent, it can't be replenished until summer when these winds die down.
The profile that we have right now doesn't show that the ozone hole has completely closed. It shows that the area where the ozone hole usually appears is starting to fill back in.
And what is the reason for that?
That's because the polar vortex, the winds that set up over the pole, are now starting to break down. Compared to last year, the ozone hole is filling back in at a much slower pace. Last year, the ozone hole appeared very quickly, stood there for several months, and then filled back in very quickly. This year, it's staying around a little bit longer, and it's filling in a lot slower.
What is the reason for that?
We don't know yet. It's too early to tell, really.
Okay, now why do you spend all that time measuring air where no one lives? People don't live here. Why don't you measure the air in, like, say, San Francisco or something? Why do you come down here to do this?
In order to know how polluted or how much ozone is over, say, the United States, you really got to know what the background level is, what the normal background level is for the rest of the world, and that's what you get at the South Pole.
What is the basic essence reason that you're out here doing this?
We're trying to see how Antarctica is so unique today in terms of its climate, and it's undergone such a dramatic climate shift. We're trying to piece together what's happened to it and the course of events that led us up to today's present situation. When you look at how things have changed in the past, you can look forward to the future and see how events may again change. Antarctica may again be warm someday. We don't know.
Huh. There you go. You can measure ozone depletion. So hopefully we have have fixed that problem, but they're still going to keep measuring it just in case, because that's a big problem. Another problem associated with high population is what we call overexploitation. That's overfishing, overhunting, and that sort of thing. Especially in marine biology, we worry about overfishing. It used to be, it wasn't that long ago, less than 100 years, that the cheapest thing you could eat was seafood. Now, if you want to go eat seafood, that's expensive. You know, that's high. You know, people used to frown. You know, oh, you're going to eat fish. You know, what a lowlife. He has to eat fish. I'm going to eat beef. Nowadays, it's like, oh, you're having fish for dinner. Wow, that's good. That's expensive stuff. It's become rare to have seafood, and one of the reasons why is overexploitation. Much of the marine fish stocks, that's what this graph is showing, have become what we call overexploited or crashed. If you look at this graph, as we go to the right, we're going up in years. And you can see 50%, over 50% of fish stocks have been overexploited or crashed. There's only maybe, 30% there of fish stocks remaining that aren't overexploited or crashed. That means overexploited means overfished, where there's hardly any left. Fully exploited, almost everything. And there's nothing underdeveloped left as far as our marine fish stocks go. There's just not much fish in the sea, is what these graphs are saying. And you can see here another graph. Are you with me, Stephanie? Appears that you're not. You can see here the population of fish in 1900, and this is the red means a lot of fish basically, and the green or the light blue means not much fish. And you can see this is the coast of the United States here, and you can see there were a lot of fish, especially in the northeast waters here, and now the fish stocks are much lower. So that in 100 years we've lost most or all of our fish. A lot of it's due to pollution. A lot of it's due to habitat loss, filling in the marshes and stuff. But a lot of it's also due to overfishing. Because we've developed ways to catch a lot of fish. Huge nets can be dragged across. Look at all the fish in this net. When you remove fish from population like this, they just can't rebound fast enough. And so what you're seeing is, I think when I was a kid there were 300 shrimp boats. Or maybe I have this wrong. 900 shrimp boats in Georgia operating. And now there's 300. I think that's what it is. So we've gone down in our number of shrimp boats a lot just in the last 20 years. The shrimpers just, there's not enough food out there for them. And so I've noticed it. My dad and I used to go fishing offshore. And we'd catch, if we went offshore fishing, we'd catch 10, 12 kingfish sometimes, king mackerel. And if we go out now, we might catch 1 or 2. There's just less fish out there. Once you catch the big fish, you have to go for smaller fish. And once you catch those, you have to go even smaller. We call this fishing down the food web. And that's what we're getting smaller and smaller fish, because the big fish are pretty much all gone. So you look at all this, and a lot of people look at this and feel like they're under attack. When this is presented to them, they say, I'm not doing anything wrong, I'm just living my life as normal. And I think the best thing to do is try and get past that and say, okay, there's a problem out there. What can be done about it? Let's look to see what can be done to fix this. And so here is some of the things, for instance, that could be done to lower the carbon dioxide levels. I mean, let's face it, we're not all going to start living without our cars and without our air conditioning. That's unrealistic to ask people to do that. So what can be done? Well, here's some of the things. Stop deforestation. When you put your trash in the recycling, you're not having to cut down trees anymore. And if you're doing emails instead of using envelopes to mail things, you're helping save the trees. So we're moving towards that. Stopping deforestation, more efficient cars. You're going to see electric cars whether you like them or not. That's going to be the thing because they're so much cheaper. Most people will spend a couple $1,000s a year on gas. That's a lot of money. And, over 10 years of driving your car, if you spend $2,000 or $3,000 a year like most people do, how much is that over 10 years? It's $30,000. That's enough. That's the whole car or more. So we're going to see more efficient cars, and pretty soon most cars will run somewhat off electricity, if not completely off electricity. That's coming. Driving less, I don't know if that's ever going to happen. It could. Try to walk more. Carpool, that kind of thing. Biofuels are coming. This is making gas out of corn and things like that. That can be done. And we already use 10% ethanol. Have you ever seen the sticker on the gas pump that says 10% ethanol? That's from corn. They grow corn and they can make that into gas. So biofuels will help. Instead of digging up the fossil fuels, biofuels use a lot less carbon. They'll release a lot less carbon.
Well, ethanol is like alcohol.
Ethanol is alcohol, and that alcohol is made from plants. That's a biofuel. More efficient power plants, we're definitely seeing that come around. Storing the CO2 from power plants. We have the ability right now, all the exhaust that comes out of a power plant, you can put filters on it that'll trap the CO2 and put it away and store it away so you don't release it to the atmosphere. We can do that now, it's just expensive. And so if they came to you and they said, hey, we store the CO2 and not contribute to global warming, but your electric bill is going to be $20 more per month, would you say yes or would you say no? Most people would say no. But the problem is, seeing into the future and going, okay, this is going to cost me a lot more in the future if I have to pay more insurance and that sort of thing from all the effects that global warming is going to have. Paying more for food, paying more to clean your air later. Nuclear power. Nuclear power produces no carbon dioxide emissions. It's clean energy. The only thing it does produce is nuclear waste. Now, nuclear waste has gotten a bad rap. Nuclear waste can be stored and put away, and to me, nuclear waste that can be stored and put somewhere, I mean, it's going to be toxic for thousands of years, but at least it's under wraps. Better than the carbon waste that's in the air already affecting the climate. More wind power.